So hello everybody and welcome to another session of the IFIMAC plus ICMM joint seminar series. My name is Elsa Prada and I will be chairing this talk. Behind the screen we have Maria Jose Calderon hosting this session. As usual, the session is being recorded and will be made available later on YouTube. You can ask questions during and at the end of the talk by raising your hand or writing them in the chat. Today, it is my great pleasure to introduce our next speaker in this series, Anton Akhmerov. Anton is a theoretical condensed matter physicist working in the areas of graphene, topological insulators, and Majorana bound states. He did his PhD at Leiden University in the Netherlands in the group of Carlo Beenakker. He finished in 2011 and then went to Harvard University as a Golub postdoctoral fellow. Finally, he moved to Delft University of Technology in 2013, where he works as an associate professor. In Delft, at the Department of Quantum Nanoscience and QuTech, he leads the Quantum Tinkerer group together with Michael Wimmer. Among his various research areas, he has also specialized in numerical simulations. Actually, to make the numerical calculations more accessible to the community, Anton and his colleagues have developed a software package named Quant, which can be used to numerically solve a broad range of problems in mesoscopic quantum transport. To finish this introduction, let me tell you that Anton and his collaborators have an online course on topology in condensed matter that is very complete and interesting. You can check it out in his webpage. Today, Anton is going to tell us about Josephson versus Andreev. What can we do with only tunnel junction circuits? So please, Anton, the floor is yours.
Thank you very much. And also thank you for the invitation. It's a pleasure to see a lot of familiar and also new names in the list. So let us begin. Most of the work that I'm going to talk about is not extremely new. It was mainly finished in 2021. But still, I personally find the moral of the story also illuminating, and this is a bit of the message that I want to convey. And of course, I have to say that a lot of conceptual insight, if not majority of the conceptual insight here, comes from my collaborators. Vala was the one who invented essentially the whole story of the first work I'm going to talk about, and Andrei both did Vala is now in Cornell. Andrei is a PhD student in Delft. He realized he taught us basically how the other thing works. So also, if you're interested in trying things out in more detail, both of these works do come with a source code. Also, thankfully, unlike a lot of my other works, this stuff is fairly easy and straightforward to run. It doesn't require a cluster. So if you want to play around with it, do check these out. All right, and also, like I said, I'm like Elsa announced, I actually welcome questions at all times. So please, if I go too fast, do interrupt. I think the explanation. I'm happy to provide extra details. So let's begin, and we begin with an important divide. So I'm not sure if you are aware of this, but our field, the condensed matter physics and quantum physics, actually divides into two. There's fermions and there's bosons. These two branches of quantum physics do not really overlap, and they have their identifying traits. So first of all, fermions are there to stay. You cannot create a fermion out of nowhere. It's a physical thing. You can check it out. Fermions also, there's a lot of rich physics associated with them. Like a lot of the entire quantum materials community is due to interacting behavior of many fermions. These are the excellent things, and this thrill of exploration is what attracts us to them. But fermions are not without a downside. They are messy and they're hard to control. On the other side, the bosons, well, they're a completely different beast. First of all, the bosons will eventually decay. And also, if you're studying bosons, typically your life is quite a bit more relaxed. They're nice, they're understandable. The Hamiltonians that you write down work. That I cannot say it's true for all the fermionic systems. If anything, I would say bosons are maybe a bit boring. And I am personally, so there's the big divide, and different people prefer different things. I am pretty much the fermionic guy. Also, just to make it absolutely clear, this is not a very serious, so there are true parts of the statement, but it's not a very serious comparison. There are also hard to understand problems in bosons, but still, I think to an extent this is there's a share of truth in it. So I said I'm very much a fermionic guy, except for today. So this is a story about the interaction between these two fields and how we can balance between them. So, well, of course, to explain what this is about, I'll need to tell you a bit more about the subject of our today's study. So I'll mostly focus on, actually entirely focus on Josephson junctions. So any Josephson junction is a weak link between two superconductors. So here you see this weak link. The superconductors could have a phase difference, and there is a supercurrent flow from one side of the junction to another, with some maximal value of the critical current that's reached at a specific value of the superconducting phase. That's pretty much how they work. It's an absolutely brilliant piece of both technology and a wonderful physical system to study. But now we are going to think a bit what you can do with these. And for that, we need to know that there's the standard bosonic boring Josephson junctions, which come with a tunnel barrier so that there are no single particle excitations in the system. And the current phase relation is proportional to the sign of the phase difference. However, there are also the fun fermionic Josephson junctions. This is where we replace a tunnel barrier with some normal region. And then there are single electronic states, which have their own dispersion relation with the phase. It's periodic because the phase only enters the Hamiltonian as well, a phase. But now, because there's so much more variation of what one can put between the two superconductors, there's quite a bit of physics associated with these. So I'm not going to talk about just Josephson junctions. I'm going to talk about multi-terminal Josephson junctions. And these in particular are much easier to make if you have indeed a normal region, so that the electrons or any quasi-particle can couple to more than two superconductors. Now, why is it special? We don't know yet, but at the very least, we can see that there are no more options. The particle could go here, it could go here. There are more control parameters, and in manipulating and in learning about quantum systems, control parameters are, of course, great. So let's see what we can achieve by using a multi-terminal Josephson junction with a mesoscopic electronic system in between. I personally was interested in this system already a whole while back. because turns out if you have more control knobs, you can control the spin splitting in the system. And you could make the superconducting phase difference act as effectively as a Zeeman field, and you can even push some of the Andreev levels through zero. But that's not the end. That's not the end of the story. In an absolutely beautiful later work, this collaboration in most of these people were then in Grenoble, and Yuli Nazarov is my colleague from Delft who was at that time visiting Grenoble. They demonstrated that if we view the Hamiltonian of this junction as a of the states in this junction as some Hamiltonian as a function of parameters, one can cause a topological phase transition. So one can have the band at a negative energy cross with a band of a positive energy, and one can create band structures which have a non-zero Chern number, so that are somehow similar to quantum Hall insulators. So here, importantly, this is not a precise metaphor, because our Hamiltonian is a single, is a few particle Hamiltonian. It's not an extended band, and the equivalent of the momenta in solid state systems is now played by superconducting phases. Still, it is quite peculiar that this can happen. And then finally, another another unusual phenomenon that occurs if we allow electrons to travel across multiple junctions is that we can now generate so-called multiplet supercurrents. These are processes where one electron from a lead goes to another lead. Andreev reflects, so a hole travels to a third lead. Andreev reflects again, and after completing this loop, what happens is that two Cooper pairs from different terminals enter a third one. And a special feature of this process is that it can have finite voltage. Energies of these Cooper pairs are equal. Then the total process costs no energy transfer. So this is like a supercurrent flowing at a finite but commensurate voltage, and it involves not just two electrons forming a Cooper pair, but more, and it is enabled by this complicated manifold trajectory consisting out of multiple parts. So all in all, multi-terminal Josephson junctions are a clear win for Team Fermions, which, once again, as a Fermion guy, I really appreciate. It's nice, and I really love these systems. So now in the next part, I'll need to go into a bit more details. So let's examine the spin splitting. Bosons don't have spin, so that's a bit out. But let's look at the consequences of the topology in these band structures. The basic idea here works as follows. It's a little bit like I explained. We have a normal scattering region attached to multiple superconductors. We define an effective Hamiltonian, which is a function of all the phase differences. This Hamiltonian could have topological phase transitions where the bands different bands touch at zero. These phase transitions, if I view like cross sections of the three-dimensional Brillouin zone, separate regions with a finite Chern number. And what is a quite impressive consequence of this topological change is the quantization of the transconductance. Basically, if I fix one of the phases such that I'm in an interesting plane in the parameter space, and I start varying two others by applying some constant but arbitrary voltages, turns out the currents that flow across these two terminals are quantized due to some self-averaging of the Berry curvature, the vanishing of the adiabatic corrections. This is a little bit technical, that conductance quantum emerges is quite unexpected, especially since supercurrents can flow without any limits. Still here, this is the case. All right, so that's the fermion story. Now, shortly after that paper was published, my friend and colleague Vala Fatemi, and I remember this conversation rather clearly. I was visiting MIT, and he said, we were walking for lunch, and he said, "Hey Anton, do you think we could be able to make such a junction, but without Andreev states? Can we perhaps use Josephson circuits?" And to me, this perspective was quite surprising, because obviously fermions are necessary because we are, of course, working with the Andreev states. But it was, of course, the correct idea. So let me explain how it works. For that, I need to introduce the Josephson circuits and the bosonic part of the story. So unlike with the fermionic circuits, where a lot of details matter and you can and you need to understand the microscopics of the system, Josephson circuits don't have a lot of building blocks or variation. They are combinations of the tunneling Josephson junctions. So that's this very basic one with a universal current phase relation, and capacitances. Capacitances just because, you know, tunnel barriers are effectively parallel plate capacitors, and pieces of metal are capacitors. So we do need to keep track of where the charge is going. So the Hamiltonian of these devices, the capacitive Hamiltonian, is equal to charge square on the capacitor times the charging energy, minus an offset charge, which is set by the gate voltages. Of course, if I apply gate voltage, I can make a different number of charges on an island have lower energy. The Josephson part of the Hamiltonian is also fairly similar to what I've shown before. Shown the current phase relation. The Josephson relation is that the Josephson energy is equal to some prefactor Ej times the cosine of the phase difference. And once again, there is a control knob. If we make a loop, we can apply a phase offset by threading magnetic flux through that loop. Now, this is a quantum mechanical system, which means the two quantities, n, the number of Cooper pairs on an island, and phi, the phase difference of the island, do not commute. In fact, their commutator is equal to I. So in other words, these act like a momentum and coordinate operator in quantum mechanics. This idea is decades old. It was extremely surprising when it was identified how one can make single particle quantum mechanics with collective degrees of freedom, but now it's fairly established, and these circuits are a standard building block for all superconducting qubits and for other animal-inspired devices like squids and snails. And this is not a joke. Both are circuits combining several Josephson junctions. All right, so now we have the building block. Let's try to understand how these circuits work in general. And this was quite illuminating to me. So let me try to explain what symmetries the Hamiltonian here may have. So first of all, there's the flux periodicity, namely only phases enter the Hamiltonians. If we increment an external phase by 2 pi, we get the same Hamiltonian. There's also, and this is a little bit less intuitive, charge periodicity. So adding a Cooper pair to an island. So if we increment a number of if we apply a voltage required to attract another charge on the island, and we replace the charge operator with n+1, we will still get the same Hamiltonian. So these are like translation symmetries in phi space and in the charge space. Well, one is due to fluxes being entering the Hamiltonian like a phase, the other one being due to the charging energy being quadratic in the number of charges. Regardless of what you try to do with the circuits, they have two properties. There's the time reversal. So if I write any Hamiltonian by using the rules that I have described, which is a function of an external phase offset and the gate charge, and they complex conjugated, I will get the same Hamiltonian, but the phase offset will change sign. This is extremely similar to how time reversal works in quantum mechanics. It is complex conjugation, and momentum-like variables change sign because they are in fact complex phases. There is another property, and that is charge inversion. Namely, if I write a Hamiltonian and I replace both phases and offset charges with their opposites, I get the same Hamiltonian back. And I list both of these symmetries because these are important. So in order to create a band structure with a finite Chern number, one needs to remove these symmetries. How do we do this? Well, so first of all, the periodicities of both variables define an effective Brillouin zone. But then keeping some of the variables phi and ng fixed and varying the others makes the Hamiltonian looked as basically cross-section of a larger parameter space, breaks either time reversal or charge inversion, depending on what we try to do, and allows us to have enough freedom to implement anything we like. All right, so these are the rules of the game. Let's try to see them in action. So what are the minimal topological circuits? And the answer here is straightforward. We need at least one parameter to make at least one control parameter so that we break at least one symmetry. And we need at least two more to define a two-dimensional Brillouin zone and to have a finite Chern number. So there are only two circuits that do this. One is 3 Josephson junctions put in a circle like this. So here you see these crosses are in a square, which means that these are elements that combine both the Josephson energy and energy. That's a circuit symbol for both. This circuit is well known. It is called the flux qubit. It's one of the first superconducting qubits that really worked well, or sufficiently well. The other circuit also requires three parameters. So here we have 2 offset charges and 1 phase because there's 1 loop. The alternative circuit is 1 offset charge and 2 loops. So here we have 3 junctions coupling to the same island. This circuit is also one of the earliest superconducting qubits, and it is called the Cooper pair box. They are well known. And well, turns out that the accidental degeneracies at charge offset that were also known for a while for either of the circuit actually are topological phase transition points. And these mark the points where the Chern number of this effective band structure changes. And turns out there's also a topological response associated with these. There was a nice work by one of the authors of the multi-terminal Josephson paper that explains that in this circuit in particular, it acts as a topological switch where you can send current one way or another depending on the ratio of the different Josephson junction strengths. So the idea works, but of course this is not quite the same because here, unfortunately, it's impossible to observe quantized conductance in these circuits because due to the overall symmetry of the effective band structure, it's only non-trivial if we mix charge and phase as 2 parameters, and this does not give us a conductance quantum because this mixes a current response and the voltage response, so the topological properties end up dimensionless. A more complicated circuit, however, the one which only uses fluxes and control parameters requires requires a bit more elements. So here you see a single loop with an external phase bias, and there are two arms to which we apply voltages. This is effectively like making the phase advance through this Brillouin zone. So it turns out such a circuit indeed works exactly in a similar way as a multi-terminal Josephson device, in that it has topological phase transitions. And in the regions where in the regions between the topological phase transitions, the Chern number is non-zero, and we have a quantized transconductance response. Now, just like the other device, this one is probably fairly hard to make and somewhat flimsy. There's a lot of detail, so this is not quite a superconducting standard for the current voltage yet. But one may explain. One may think about whether this device could replace the whole resistance standard. And this work so we were in contact with the authors when wrapping up the manuscript. They were more focusing also on the quantization aspect. All right, so let's see what we learned. We learned that Josephson circuit implement the topological have points where the band structure undergoes a topological phase transition. That's the while points. And they have regions in the parameter space where they have a finite Chern number, and therefore, just like the Andreev circuits, they have a quantized transconductance. Very good. That seems to balance fermions and bosons out a bit. And for me, it was a big learning experience. I realized that maybe I've been looking at the world too narrowly and being dismissive of the bosons too much. So shortly after we wrapped up, we started wondering about the other thing that I mentioned, the multiplet current. So let me give some background here, because this story is also a fair bit older. So I have already explained that there is a complex process that carries multiple Cooper pairs, but the formal requirements for a multiplet supercurrent are the following. So first of all, we need 3 superconducting terminals. Now, if the voltages that we apply to one of these we can always consider ground. If the voltages applied to 2 of these terminals are commensurate, so n times V1 plus m times V2 equals to 0, then there is a process that allows to transfer n Cooper pairs from one terminal and m Cooper pairs from the other terminal that gives exactly 0 energy cost. And therefore, this process carries an enhanced current. So if one makes this circuit in a lab and measures current as a function of 2 voltage biases, one observes a local maximum in the current. The situation is a bit more complicated because there are all the other processes that can also carry current at a finite bias. So unambiguously seeing a quartet supercurrent is fairly tricky. So there is an experimental search for these devices, and there's a series of works that have clearly observed the quartet supercurrent. So let's take a look at these. So first of all, this one is in I think in a 2-dimensional electron gas. It's a 3-terminal Josephson junction. So here we see the voltage biases. There's the supercurrent that goes between 2 of the terminals, a supercurrent that goes between the other 2 of the terminals, yet another supercurrent that goes across these 2 terminals. These are all the boring 2-terminal supercurrents. But there's also a clear maximum in the current, which we see in the differential resistance, that is diagonal and goes the wrong way. So this is the quartet supercurrent. And moreover, there are fainter lines corresponding to other quartet supercurrents, other multiplet supercurrents. Now, there was another work from Weizmann from the group of Moti Heiblum. This one used a nanowire, and also here we see just likewise peaks that correspond to current flowing, to enhanced current flowing across multiple terminals. And yet another group. This one was from the group of Philip Kim, and this one was using graphene as the terminal. So also in this work, an additional peak for corresponding to the quartet supercurrent was observed. So all is good, but now here you should, of course, if you are following the talk, you realize that now the question is, can we do the same without multi-terminal Josephson junctions by just using a circuit? So let's ask. So here, this was not my most creative moment. So we asked, what is the simplest circuit that can at least in principle produce the correct behavior? Right? It has to have 3 superconductors. So these are the 3 junctions. So it has only one node, one island that is decoupled from everything else. So for completeness, let's also add the capacitive energy. So this is really the minimal circuit where this phenomenon is at all defined. It do need 3 superconductors. So does this work? Let's see. So the recipe in such a circuit is the following. So we have the Hamiltonian as a function of 2 phases of the superconductors. So we compute a map of the current flowing into the ground as a function of the 2 phases. You see here this map. Then in order to define, say, quartet supercurrent, we make either of the both phases wind with the voltage. So there's the phi1 is equal to V times T, phi2 is equal to phi2 of 0, this is a typo, minus V times T. So basically, the phases at commensurate voltages make this loop, infinitely repeated loop through the Brillouin zone with a constant period. To determine the quartet current, we compute the average current that flows into the ground terminal. So we go along this line and we compute the average. So, well, I mean, we do see the answer pretty much already right now. It works. So there's more red on this path than there is blue. So the average current is positive. So it checks out. If we compute the average current on along this curve as a function of the offset, the initial phase difference, we do observe a slightly non-sinusoidal, but still a very much non-zero signal. So the simplest possible circuit did, after all, work and did show the quartet supercurrent. However, there's actually an even more fun trick here. And the trick is that I was showing the behavior of a classical circuit. So here, not only did I take the 3 Josephson junctions, but I also said, well, the capacitance of the middle island is just infinite. So it's effectively another massive superconductor. So it's not a circuit where the charges are quantized and phases do not commute, but it's a large. So you should imagine a large chunk of the superconductor where things just flow. The reason why this device works is the nonlinearity of the current phase relation. So basically, trigonometrically, if we minimize a sum of a bunch of cosines, we will find a complicated answer. And it turns out this answer is sufficiently complicated that to give a non-zero average. So, and people have tried classical circuits already for a while. So afterwards, we started looking back in the older literature, and we found this work from May 1977. This is a bit more than 54 years ago. These are, you can see this sample is not beautiful. It's not nanofabricated like modern samples. There are thin lines with superconductors here, but that's pretty much it. So the authors the authors did see quartet supercurrent. These are the extra resonances appearing at commensurate voltages. And they interpreted them as basically a propagation of quasi-particles across this bridge. So they did still have they did still conjecture that the mechanism for what they see is microscopic. But we now know that in principle, the circuit itself is prone to give rise to this effect. But this is, of course, okay. Let's go a little bit further in time, and let's say the classical circuits are probably not extremely exciting. Let's think whether we can come up with quantum effects. So for that, let's look at the opposite limit when the charging energy, so the capacitive energy, dominates, and we really see a single Cooper pair on the island. So here there is the low charging energy limit. This is the result that you've seen so far. This is the closest analog, the critical quartet supercurrent, which we plot here. And we see that if we do increase the charging energy, then all the way to the deep charging regime, the quartet supercurrent stays constant. And moreover, if we make the two states of the middle superconducting island degenerate in energy, so we have the state with n Cooper pairs and n plus 1 Cooper pair equal in energy, there is not even a suppression. So of course, we realize that in that case, charging energy drops out of the Hamiltonian. And we see a constant supercurrent, a constant quartet supercurrent that doesn't actually care about the capacitance at all. Now, funnily enough, also, this is the deepest quantum limit that is possible to get, because at every point in time, there is just one coherent Cooper pair that is participating in the process. So in this regime, of course, there's no doubt that this is a quantum phenomenon because we only allow 2 electrons to carry the current. Since this is a quantum mechanical Hamiltonian, one can also think a little bit more in the direction of the non-adiabatic effects that give rise to the transconductance in the case of the multi-terminal Josephson junctions and to the conductance quantization. And turns out very much by a similar logic, these effects also give rise to a finite response in this circuit. Namely, if we apply a finite voltage, there's a quartet current flowing through the circuit, which is proportional to the conductance quantum, a superconducting conductance quantum, which has 4e square instead of e square, times the voltage. And there is indeed a correction. The difference between adiabatic and the non-adiabatic correction is that the non-adiabatic one is proportional to the voltage, so it looks like a resistance of this device. And now yet another thing that brings the two topics somewhat closer about the system is that in the high charging energy regime, the circuit is actually has exactly the same Hamiltonian, meaning the math is exactly the same as a single electron quantum dot. So if we make a quantum dot and we make it tunnel coupled to 3 superconductors, the Hamiltonians will look exactly the same, because in fact, it doesn't actually matter whether the 2 degenerate states are n Cooper pairs and n plus 1 Cooper pair, or whether these are a quantum dot with an electron versus a quantum dot with a hole. So turns out in order to create a multiplet supercurrent, one does not even need to try very hard. If one looks at a single particle level, Cooper pairs behave very similarly to single electrons. Now we wrap this work up sometime summerish 2021. And there was a bit of a back and forth. Since this is on SciPost, you can read all the reviews. what the referees think, what we reply. So, so we were arguing that these devices are simpler to make than the mesoscopic circuits because these are using standard elements and these are much easier to tune. The referees were disagreeing with us claiming simplicity because, you know, this is usually a fairly opinionated statement. But we have managed to explain why we indeed believe this that these circuits are probably easier to observe. Something, however, that we did overlook, we learned only fairly recently. So this is a preprint which appeared on Archive April 2022 by the group of and these measurements were done by the group of Gleb Finkelstein. So these are multi-terminal graphene Josephson junctions. And here you see they do have the quartet supercurrent. No, this is the quartet supercurrent. So this is all very much like the Andreev circuit, except, and this is something that we completely overlooked, I have to say, the authors realized that essentially the entirety of the quartet supercurrent that they observe is not due to the complicated trajectories of electrons going across the arms of the device, but this is rather due to the individual junctions in the circuit coupling to each other now inductively. I did not touch this. We did not contain any kind of. We did not use the most general description of these elements. But if one does include a shunt resistor, and if one does include an inductance, I believe, of the circuit, these still give rise to a quartet supercurrent. So now you may ask, why were the authors so certain about it, that the quartet supercurrent here is carried due to the circuit physics and not due to single electron physics? And the answer is twofold. First of all, circuit physics, unlike electronic physics, are much easier to simulate. This is you need to solve one few component ordinary differential equation. For quantum physics, you need to diagonalize the Hamiltonian. You need to know the microscopic parameters and a lot of other stuff. So this circuit turns out to be reproduced by simulation rather well, on the one hand. On the other hand, if you carefully look at how the device is made, you'll see that the middle, where the point where the three superconductors come together, is very small. So the entire physics is should largely be dominated by the behaviors of the individual arms of this thing and not by the behavior of the middle. So these two facts combined did allow the authors to indeed conclude that quartet supercurrent in this experiment was due to the circuit physics and not due to the physics of Andreev states. All right, well, actually I seem to be quite okay on time, but I'm already at my conclusions. So far I have explained, first of all, that the multi-terminal Josephson circuits, that they are quite a bit of fun and they allow us to implement a bunch of things. They are easier to control and to understand than Andreev circuits. Now, to be completely fair, I did not make a systematic comparison here, but I have demonstrated the level of reasoning that goes into it, and believe me, they are easier. The multi-terminal Josephson circuits implement controllable quantum mechanical Hamiltonians that have topological band structures, which is a fact that was so halfway between known and unknown, so for me it was certainly unexpected. And finally, they carry multiplet supercurrent. So this would be it, but since I also have some extra time, I hope I have a bonus story for you, and that is about a supercurrent diode. Supercurrent diode is a field that exploded in the last couple of years. The basic idea here is that if you take a an Andreev or a Josephson junction, so with Andreev states, and you break time reversal and inversion symmetries, then the current phase relation becomes non-reciprocal. So this circuit behaves like a diode in that it lets supercurrent pass easier one way than the other. And just a couple of days ago, last week, in fact, my colleagues ran an online workshop. I don't think the videos are available yet, but they will be soon. And you see a whole lot of works, these are both theoretical and experimental works, exploring how quantum materials enable this superconducting diode effect to occur. And here, of course, we need, these are frequently a combination of spin physics due to Zeeman field, and there's inversion symmetry breaking. So you could see how mesoscopic physics could play an important role here. So do check out the workshop program. It's a virtualscienceforum.org/Josephson diode. Some of you may have seen it already before. And these are all interesting works. There are really creative ways. In particular, I could recommend this work by Liang Fu, Universal Josephson Effect, about how one can boost Cooper pairs and create unidirectional supercurrent flow. But also many of these other works I found quite interesting and educational. But you could guess where I'm heading now. As I was learning about the superconducting diodes, I of course asked whether a circuit can do it. And we actually started a project, started exploring what we could do. And we were extremely enthusiastic until actually Vala did a more systematic literature search, and he came up with this conclusion. Not only a circuit Josephson diode, a super Josephson circuit can make a Josephson diode, it already did. So specifically, we found this paper from 2014 about new AC-powered single flux quantum digital circuits that observed that two Josephson junctions in series with the inductance make a diode. Over here, you could see that critical current one way is larger than the critical current the other way. This is 2014. But we still went deeper. This paper is from 1967. So this is, I'm now giving this talk almost at the 55th anniversary of the publication, of the submission of this paper. It's a planar Josephson junction where the authors apply magnetic field and they say, look, the critical current is highly asymmetric. That's an unusual Josephson physics, and but we understand it. It's because of the junction asymmetry. There is more critical current flowing on one side or on the other side. This is also a Josephson diode. So let me put this back into the context of my presentation. So first of all, I hope I have explained some part of my excitement with the Josephson circuits, that they implement a bunch of things. But I also importantly think, looking back at what I extracted from this field, better understanding Josephson circuits, so the macroscopic physics, teaches us to isolate and refine isolate the electronic phenomena and refine our understanding of quantum materials. So I hope you find this a useful perspective to yourself as well. So on this, I conclude. Do you have any questions?
Thank you very much, Anton. Thank you very much. So now we are open for questions. And I see one already from Akashdeep. Can you unmute yourself? Yeah, please
Sure.
go ahead.
Hi, Anton. Good to see you here. Thanks for a very nice talk. I was a little bit confused with why are things periodic in the charge, because it's a parabola, because parabola does not imply periodicity, right?
Oh, Yeah, let me see. That's this bit. So things are periodic. So the charging in the parabola is of course not periodic with charge, but we ask how the Hamiltonian changes as we change the offset charge. So and here you see that this is n minus ng. So if we basically it's a bit about the linearity of the capacitances. If we attract an extra Cooper pair on the island and replace the counting of the Cooper pairs by starting from a different value, the Hamiltonian looks the same. Now, in a realistic system where the electronic physics also plays a role, these two states are not exactly the same. And n Cooper pairs is fundamentally different from n+1 because, you know, Cooper pairs are composed of electrons. Electrons have a chemical potential. It changes. And the charging of a mesoscopic device is nonlinear. However, those effects are negligible, and indeed, physics of n Cooper pairs and n+1 Cooper pair is almost exactly the same to I think a degree that the nonlinear effects are not measurable in superconducting circuits. Also, a bit to comment on this, to extend beyond, if one considers especially out of equilibrium circuits and uses mesoscopic materials, like mesoscopic materials do have nonlinear capacitances. Those do break periodicities, do break this charge translation invariance, and give rise to different, also quite peculiar physics.
Thanks.
So more questions, please. Well, while people start thinking, I wanted to ask you to comment a little bit further. In one of your slides, you had the statement that non-adiabatic corrections due to Berry phase curvature. So can you elaborate a little bit more on that?
Yeah.
What do you mean with the non-adiabatic corrections?
Yep. So here the way how could I say this? So first of all, let's start with what is happening here. We have a Hamiltonian that depends on two parameters, phi1 and phi2, and and the Hamiltonians at different points, of course, do not commute because the parameters enter in a complicated fashion. So that's why, in the first place, the Berry curvature does appear. So now, how Berry curvature relates to the current. This is explained in quite a bit of detail in the paper of Nazarov and his co-authors introducing the quantized transconductance. But roughly speaking, what we need to do here is in order to determine the relation, we need to compute the expectation value of charge carried through a terminal, so of current flowing through a terminal, given a time-dependent given time-dependent values of the parameters, right? So you could imagine I could write down the current operator. I could compute at each point instantaneous state and the expectation value of the current operator, and then I could do a series expansion in the orders of the derivative of the parameters. So the 0th order term is the static supercurrent. This is dE d phi. The higher order term turns out, well, so you could see how that one could relate to derivatives of the eigenvectors because the faster we move, the more corrections the wave function accumulates. And that one turns out to be proportional to the local Berry curvature. So it's on the one hand a surprising relation, but on the other hand, it's also not very surprising because that's what Berry curvatures do. They are appearing in as a non-adiabatic effect in time evolution.
Okay. Okay. Thank you. Yes. There is another question by Antonio Manesco.
Hey, Anton. Thank you for your talk. So I was thinking, I'm pretty sure that I heard you and Valet talking about it at some point, but I don't remember. So you have those vial band structures. So what would be necessary if you want to do something like a topological insulator or something like that? Would that even make sense in the first place? And if so, what do you need to do that?
Yeah, so let me find the band structure. Let's see, that's this one. So one can make this game more complicated. So we have effectively what is known as a Weil semimetal, a three-dimensional Brillouin zone with 4 Weil points. Now, one could go beyond that, add more parameters and vary the symmetries. So for example, it is possible to create Weil rings. So loops in parameter space where two bands are degenerate in energy, and these are protected as well. Now, when you say topological insulators, however, I assume you also are thinking about things like quantum spin-Hall effect. And that part is actually quite an interesting question, but one to which I don't know a good answer. Because you see, let's get back to the symmetries of the circuit. The time reversal that we have over here is what is known as the spinless time reversal symmetry. So it's complex conjugation, but the operator squares to +1. To create a topological insulator, one usually needs a Kramer's degeneracy. So a time reversal symmetry with an operator squaring to -1. One can fine-tune systems to this regime, and this may be possible. But I don't think this degeneracy arises naturally. However, that's not the only way for degeneracies in the spectrum to appear. One could also consider crystalline symmetries, like the rotation of the Brillouin zone. And you could ask here, but what is a crystalline symmetry in the system? Because there's obviously no space in which one would want to rotate. That's not quite right. The crystalline symmetries here amount to changing the basis from, so changing the elements of the circuit. So these turn out to be spatial symmetries of the circuit. And in particular, if we look at the Weil circuit and we consider what happens if all the junctions are exactly the same, turns out, so first of all, this is one of the early proposals for a protected qubit. I think it was called a tetrahedron qubit or something like this. It realizes a double degeneracy due to the spatial rotation symmetry of the circuit. That's in the qubit literature. In condensed matter literature, this Hamiltonian didn't appear until I think a few years ago, like 2017-ish. I don't exactly remember the reference. Turns out this circuit realizes what is known in our literature as nexus fermions, a region of states protected by a band structure degeneracy due to a crystalline symmetry. So the short answer, therefore, is one can definitely create topological insulators, but not all, and these work quite nicely.
Okay, thank you.
More questions? If not, I have one last question, I would say. So it's the slide previous to your first conclusions, where you were mentioning, and I don't know if I understood that correctly, this one, no, yeah, here. So somehow, if I understood correctly, you were saying that there was a criticism that maybe this the quartet signal could be coming not because of circuit physics, but something more related to the individual junction. So my question is, can trivial effects mimic this kind of topological currents that you are describing us?
Okay, here I have to say the notion of triviality is reversed. Traditionally in this community, the Andreev physics is the non-trivial, and the circuit physics is trivial. We actually had a discussion with one of the colleagues over email whether we are really allowed to call this multi-terminal circuit a multiplet supercurrent, like whether it's genuine or not. I'm not sure how conclusive the discussion was, but at the very least, neither of the sides managed to at the very least, we were not convinced that we are not allowed.
Mm-hmm.
So here, I don't think there is a concern. Rather, the authors present. So this is a system that could, in principle, have multiplet supercurrents of fermionic origin.
Mm-hmm.
But on the one hand, the results are well explained by a circuit simulation. That's one observation. The other observation is that the device is made such that the fermionic multiplet supercurrent would be minimal, and there's actually quite a sizable one measured. So there's no concern whether the supercurrent here is of a circuit origin, but rather the authors convincingly demonstrate that even in this mesoscopic device, the circuit origin of the supercurrent dominates over the fermionic one.
And these signals should be quantized or not here?
No. These signals are not quantized. This is similar to a supercurrent, right? That's you apply a voltage and extra current flows. The larger you make the circuit, the larger the current.
Okay, I see. Very well. So, is there any other question? If not, let's thank Anton very much. This has been a wonderful talk. Thank you. And we'll see you all of us next week, hopefully.
Yeah.
Goodbye.
Thanks, everyone.